KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In continuation to the last class, in this class we start with example 7. So in our previous class we completed up to example 6. So now we start with example 7 and we will continue to discuss example 8 also in the same class. Right. First see the example 7. First there are two things, A and B. First A. For circuits used for transporting electric power, a low power factor implies large power loss in transmission. So is a statement, is a generalized statement, and this is the statement which is valid, that we have to explain. Okay, right. So for circuits used for transporting electric power, a low power factor implies large power loss in transmission. Explain. Okay, there is also B, but first I will explain you A and then I will go for B. Okay, right, because just now we discussed, just now I read and I explained you A. That's why immediately it is better to go for solution for A. See here, this formula we know, we know that P is equal to VI cos phi or IV cos phi, right? Where cos phi is the power factor. To supply a given power at a given voltage. If cos phi is small, we have to increase current accordingly. But this will lead to large power loss. That is what I square R in transmission. You know very well, when we are going to increase the current, automatically the power, see here, there is a square. So for I square is there, that is very important, you have to notice. So when you are going to increase the current according to this, that is what P is equal to VI cos phi. When cos phi is small, automatically the power loss will be maximum. That is what large power loss in transmission, because it is I square R. For current there is a square. Right, now see here B. Power factor can often be improved by the use of capacitor of appropriate capacitance in the circuit. Power factor can often be improved by the use of a capacitor of appropriate capacitance in the circuit. Explain. Okay. So here also they have given one statement, that is what power factor can often be improved by the use of a capacitor of appropriate capacitance in the circuit. Explain how it is possible, that he is asking. Okay, right. See here, B. Suppose in a circuit, current I lacks the voltage by an angle phi. You just just take it as sample, because suppose in a circuit current I lags the voltage by an angle phi, full stop. Then power factor cos phi is equal to, then power factor cos phi is equal to R by Z. This already you know. Okay, right. Now we can improve the power factor. We can improve the power factor tending to 1 by making Z tend to R. So mathematically, you know, when R is equal to Z, what happens to the cos phi, which is 1, no? Which is 1. So it's a maximum power factor. So we can improve the power factor tending to 1 by making Z tend to R. Let us understand with the help of a phasor diagram. This is what phasor diagram. Phasor diagram, how this can be achieved. See here. Right? And what is Z? You know, impedance. And what is R? You know, that is what resistance. Okay. So here what I am saying is, with the help of phasor diagram, we can understand how it is possible, how this can be achieved. Okay, right. Now let us resolve I into two components. It is I, it is into two components. One is IP, another one is IQ. Okay, what is IP? Is the component. IP is along the applied voltage and IQ is perpendicular to the applied voltage. And IQ you can also call it as the wattless component, since corresponding to this component of current there is no power loss. IP is known as the power component because it is in phase with the voltage and corresponds to the power loss in the circuit. I will repeat once again, because here important points are present and we have to understand clearly. Since in a circuit current I lags the voltage by an angle phi, full stop. Then power factor cos phi is equal to R by Z. Then power factor cos phi is equal to R divided by Z. Now we can improve the power factor tending to 1 by making Z tend to R. We can improve the power factor tending to 1 by making Z tend to R, full stop. Let us understand with the help of a phasor diagram as shown in the figure how this can be achieved. So what we are achieving here, Z is tend to R. When Z tends to R, you know, we can improve the power factor tending to 1. You know, R by R will become 1, no? That only we are expecting here. Okay, right. And let us resolve I into components. Okay, that is what IP along the applied voltage and IQ perpendicular to the applied voltage. Right, that is what happening regarding the resolving of I. Okay, now you know IQ is called as wattless component, since corresponding to this component of current there is no power loss. This is an important point. IP is known as the power component because it is in phase with the voltage and corresponds to the power loss in the circuit. Okay, right. Now it's clear from the analysis. It's clear from this analysis that if we want to improve power factor, we must completely neutralize. Okay, we must completely neutralize. See here, it's clear from this analysis. So till now whatever the analysis we got, so from this analysis, if we want to improve the power factor, that is only our wish, no? See here, power factor we have to improve the power factor, right? To improve the power factor, we must completely neutralize the lagging. We must completely neutralize the lagging wattless current IQ. by an equal leading wattless current. By an equal leading wattless current IQ dash. IQ dash. Full stop. IQ dash. Full stop. This can be done by connecting a capacitor of appropriate value in parallel, so that IQ and IQ dash cancel each other and P is effectively IP into V. Power is effectively IP into V. This can be done by connecting a capacitor. This can be done by connecting a capacitor of appropriate value in parallel. So that IQ and IQ dash cancel each other and P is effectively IP into V. Okay, right. So it is a logical thinking and getting advantage, right? Two things are present here. The intention for us is to get the advantage. That is, what is the advantage? Improving the power factor. Improving the power factor. How it is possible? Just by the use of a capacitor of appropriate capacitance. By the use of capacitor of appropriate capacitance in the circuit. But here the thing is, what we are in a discussion, how it is possible. We are in a discussion how it is possible. That is our concentration and our interest also. Okay, right. So what we are doing here, first we are assuming current I lags the voltage by an angle phi. That's we are assuming. See here the phasor diagram. So it is the current, it is the voltage. Current is lagging, no. See, current I lags the voltage by an angle phi. Okay, right. And when it is phi, right, the general formula for power factor cos phi is equal to R by Z. Here, to improve the power factor tending to 1 by making Z tend to R. Z tend to R. So Z is the impedance, no. R is the resistance. You just imagine yourself. So what is meaning of that Z tend to R? Why it is Z tend to R means, suppose in place of Z if you are writing R means, what happens to the cos phi value? Which will become equal to 1, no? Right? That only he is saying here, tending to 1. Tending to 1. Now, let us understanding with the help of a phasor diagram as shown in the figure, how this can be achieved. Right? So he is explaining that, let us resolve I into two components. One is IP, another one is IQ. Right? IP is along applied voltage V and IQ is perpendicular to the applied voltage. And IQ is also called as wattless component, since corresponding to this component of current, there is no power loss. And IP is known as the power component because it is in phase with the voltage and corresponds to power loss in the circuit. That's that is P is equal to VI cos phi, no. Cos 0 degrees is equal to 1. Cos 90 is equal to 0. So based on that we have to decide mathematically, right? So trigonometric mathematics, right? Mathematical trigonometry, right? That is the logic behind this. Behind these two, IP and IQ. Right? So these 2 points are important. I request you to keep in memory also. That is, IP is known as the IQ is called the wattless component, since corresponding to this component of current there is no power loss. IQ is known as the power component because it is in phase. Because it is in phase with the voltage. It is in phase with the voltage and corresponds to power loss in the circuit. Now, it's clear from this analysis. So whatever the analysis just now we had, it is clear that to improve the power factor, we must completely neutralize the lagging wattless current IQ. We must completely neutralize the lagging wattless current IQ by an equal leading wattless current IQ dash. This can be done, right? This can be done by equating. See, this is IQ, this is IQ dash. Okay, this is IQ and this is IQ dash. See here, right? So it is IQ dash and it is IQ. So what he is saying is, from this analysis, whatever we had just now, just before 1 minute or 2 minutes, and to improve the power factor, we must completely neutralize the lagging wattless current, IQ, by an equal leading wattless current IQ dash, because see, IQ dash, this can be done by connecting a capacitor of appropriate value in parallel, so that IQ and IQ dash cancel each other, and P is effectively IP into V. So throughout this discussion regarding the B, in example 7, regarding the B, throughout this discussion, what is our intention? To improve the power factor? The conclusion regarding the intention to increase the power factor is to neutralize IQ with another IQ dash. So to do that, we have to connect a capacitor. Of appropriate value in parallel, so that IQ and IQ dash cancel each other, and P is effectively IP into V. Okay, right. Now, next problem, that is example 8. See here. A sinusoidal voltage of peak value 238 volts and frequency 50 Hz is applied to a series LCR circuit in which resistance 3 ohms and that is what inductance, capital L, right, which is 25.48 millihenry, and capacitance 796 microfarad. Full stop. So I'll repeat once again the statement what they have given in the according to the question. A sinusoidal voltage of peak value 238 volts and frequency 50 Hz is applied to a series LCR circuit in which R is equal to 3 ohms, L is equal to 25.48 millihenry, and C is equal to 796 microfarad. Full stop. Find, there are 4 things in this example, there are 4 things to find: A, B, C, D. A, the impedance of the circuit. B, the phase difference between the voltage across the source and the circuit. B is the phase difference between the voltage across the source and the current. Not circuit, source and the current. Okay, right. C is the power dissipated in the circuit. Right, and D is the power factor. So 4 things we have to find here. So first I'll repeat the problem once again. You just please keep in mind what are the quantities they have given, what are the things we have to find, and what is the information theory what they have given in the problem. A sinusoidal voltage of peak value 238 volts and frequency 50 Hz is applied to a series LCR circuit in which R is equal to 3 ohms, capital L is equal to 25.48 millihenry, and capacitance C is equal to 796 microfarad. Full stop. Find A, the impedance of the circuit. You know the formula, that is Z is equal to square root of R square plus XL minus XC whole square. That is the formula for impedance regarding the LCR circuit. Okay, right. Next, the phase difference between the voltage across the source and the current. Next, C is the power dissipated in the circuit. And D is the power factor. So these 4 things we have to calculate. First, A, To find the impedance of the circuit, we first calculate XL and XC. Okay, because XL and XC is a part of formula, no. R value they have given directly, but XL, XC we don't know, no. So first we have to calculate XL and XC. So you know that the formula for XL, that is 2 pi nu into L, and the formula for XC, that is 1 by 2 pi nu into C. Right. So XL is equal to 2 pi nu into L, no. So 2 into 3.14 into nu is the frequency 50 Hz given, and into this is what 25.48 millihenry given. That's milli means 10 to the power of minus 3, no. So 25.48 into 10 to the power of minus 3 ohms. That is equal to 8 ohms, right? So if you complete this total process, it will give us 8 ohms, right? XL is equal to 8 ohms. Now, XC is equal to 1 by 2 pi nu C, right? 1 by 2 into 3.14 into nu is already you know that 50 into it is 796 into 10 to the power of minus 6, because microfarad, no. So micro means 10 to the power of minus 6. That is equal to 4 ohms. That is equal to 4 ohms. Right. Now, therefore, Z is equal to, this is the formula for Z. Z is equal to square root of R square plus XL minus XC whole square. That is equal to square root of, you know, R value is 3 XL and XC just now we calculated. XL as 8 ohms and XC as 4 ohms. You just substitute the values here and it will give us 9, and it is 4 square, no. 8 minus 4 means 4 square. It will be 16 plus 9, 25. Square root of 25 means it will give us 5 ohms. 5 ohms, right? Because it is impedance, no. Impedance is also resistance. That is what. But impedance is the resistance offered or resistance available or present in the LCR circuit. Okay, that is we got as 5 ohms, right? A completed. Now B. Phase difference. Phase difference phi is equal to tan inverse of formula. Phase difference phi is equal to tan inverse of XC minus XL by capital R, right? Resistance. That is equal to tan inverse of, you know, it is 4, no, and it is 8, no. 4 minus 8 by 3, right? It is okay. It is minus 4 by 3, and anyhow tan inverse of this value will give us approximately minus 53.1 degree. Minus 53.1 degree. Okay, right. Now, since phi is negative, no, this is what phi, it is available in negative. See the minus. Since phi is negative, the current in the circuit lacks the voltage across the source. Since phi is negative, the current in the circuit lacks the voltage across the source. Okay, right. Now, see. Next problem. See here. Next problem is, that is what next, because there are 4 things, no. A, B, C, D. So A, B completed. Now C. The power dissipated in the circuit. The formula is P is equal to I square into R, no. But what about I? I is equal to Im by root 2. So that is 1 by root 2 into 283. 283, right? 283 divided by 5. 1 by root 2 into 283 divided by 5. See here. So that is what we can write as 40 amps. 40 amps. Okay. So finally, power P is equal to 40 square, that is what I square into R, no. So 40 whole square into 3 ohms. Into 3 ohms. Right. So when it is 3 ohms, then it is 40 square, no. So it is like 1600 into 3. So 1600 into 3 means 4800 watt. 4800 watt. Okay, right. Next, last one. See, this is what D, no. The power factor. The formula, you know, that is cos phi. So cos phi value just now we calculated in B, no. That is minus 53.1 degree. So when it is minus 53.1 degree, that will becomes equal to 0.6. 0.6. Okay. So this is what power factor. So in this problem example 8, right. So by giving the peak value of voltage and frequency of AC source And in one LCR circuit, by giving the values of R, L and C also, he is asking to find impedance of the circuit and the phase difference between the voltage across the source and the circuit, and the power dissipated in the circuit, and the last power factor. Okay, right. So to calculate the impedance of the circuit, you know the formula Z is equal to square root of R square plus XL minus XC square. That is equal to square root of 3 square plus 8 minus 4 whole square. That is equal to 5 ohms, because it will be 9 and it will be 16. And this is what XL value and XC values already we calculated. XL value as 8 ohms and XC value as 4 ohms. So finally the impedance we got it as 5 ohms. Next B, phase difference phi is equal to, phase difference phi is equal to tan inverse of XC minus XL by R, that is equal to tan inverse of 4 minus 8 by 3, which is approximately equal to minus 53.1 degree. So it is negative, no? Since phi is negative, we can say the current in the circuit lags the voltage across the source. Across the source, right? Now see, the power dissipated in the circuit is, the formula is P is equal to I square into R, no? And you know I is equal to Im by root 2, 1 by root 2 into Im means V by R, no? R means here impedance, ma. R means here resistance, okay, right? But it is not, we should not call it as resistance. Here we have to use impedance word. So impedance is already we got 5, ma. So 238 by 5, that will be given as 40 amps. Now therefore P is equal to I square into R, no? So 40 whole square into 3, that will give us 4800 watt. Now power factor is equal to cos phi, cos of minus 53.1 degrees, that is equal to 0.6, because phi value here we calculated, no, that only we are substituting here. So it will give us 0.6, okay, right. So in this class we discussed two problems, example 7 and example 8. In the example 7, there are two things, A and B. In A we have given the reason or we explained, right, how it is possible to transport electric power, right, and a low power factor implies large power loss in transmission. While transporting electric power, a low power factor implies large power loss in transmission, that's we explained. Okay, because the current has changed accordingly, to make cos phi is small, that's why the power loss is maximum or large power loss will be available. Next in B, he is asking to explain how to improve the power factor by connecting a capacitor of appropriate capacitance in the circuit. Okay, right. So with the help of Phasor diagram, and we discussed, and there one important point is, that is we need to neutralize, we must completely neutralize the lagging wattless current IQ by an equal leading wattless current IQ dash. This can be done by connecting a capacitor of appropriate value in parallel, so that IQ and IQ dash cancel each other and P is effectively IP into V, right. In example 8 problem, in one LCR circuit they have given some values of resistance, inductance and capacitance and voltage, applied voltage and frequency also, and he is asking to calculate impedance, that's we calculated and we got as 5 ohms, and asking to calculate phase difference, right, that is what minus 53.1 degrees, and then he is asking to calculate power, and that we got it as 4800 watts, and at last he is also asking to calculate power factor, that's we got it as 0.6, okay, right. In our next class we will continue with the example 9, okay, right. Thank you.